Okay, I'm going to start section 9.2 now. We're talking about polar coordinates, and I kind of introduced that idea in the last video there. So the polar coordinate system is different from the rectangular system in that it's just a different way to plot a point. Okay, like we're so used to plotting a point xy. If you were to plot the point r theta, then basically how you're doing that is you're starting at the pole or the origin. You're going out some distance of r units on the x-axis or what we call the polar axis, and then you're going to rotate that either clockwise or counterclockwise about the pole to be able to plot the point. Then, so now that we've looked at plotting points, I wanted to show you how to be able to graph a polar equation. Now, the majority of things that we're going to be doing here when it comes to graphing is going to be graphing by hand, and then I'll show you some things on the calculator when we're done with that. So I've got 12 equations here that I'd like us to graph. Now, this may sound like a lot, okay, but the first 6 are actually going to go by really quick, and then the last 6 are going to take a little bit more time. But in the first 6, the idea is to see what the Cartesian equation is going to be, and then recognize that form, and then draw the curve. So let's get right to it. Suppose that I want to graph the polar equation r equal 3. Well, if I square both sides, r squared would be 9, and r squared, that's the same as x squared plus y squared. That's one of my conversion formulas. And so now I'm looking at the equation x squared plus y squared equal 9. Well, that's going to be a circle of radius 3, right? A circle centered at the origin. By the way, r is the radius of the circle, is another way to look at it. So it's essentially just drawing a circle of radius 3. Okay, now I talked about the polar graph paper in the last video, and I've got all these graphs here of the curves that we're going to be drawing. Basically, in this problem, it's not going to matter what theta is. Theta can be any one of these radial lines, and whatever radial line you're talking about, you're always going to go 3 units out and plot a point. Ultimately you end up getting this circle of radius 3. Okay. Here's another example. Suppose I want to graph theta equal pi over 4. Well, if I were to take tangent of both sides, okay, tangent of theta equal tan pi over 4. Tan pi over 4 is 1, and tan theta is the same as y over x. So if you have y over x equal 1, and you multiply both sides by x, then that gives us y equal x. Okay, so all I have to do here is draw the line y equal x. Well, we know what that line is, right? We're drawing a line slanted at a 45-degree angle. By the way, theta is 45 degrees, right, in degree measure. And so I've got several points on that line, but basically, it's not going to matter what r is. You're always going to be on the pi over 4 radial line. So here's like when r is 1, here's when r is 3, here's when r is 5. R could be a negative also. R negative just means that you're going in the opposite direction on that radial line. So like here's r equal negative 2, r equal negative 4, etc. Okay. Problem 3, we've got r sine theta equal 3. Well, r sine theta is the same as y. So all we have to do here is draw the horizontal line y equal 3. Okay, and so that's my third graph that I got. Y equal 3 and r sine theta equal 3 mean the same thing. Okay, here's another one. R cosine theta equal negative 2. R cosine theta is x, so x equal negative 2. That's a vertical line, and I've got that drawn here. Okay, like I said, the first 6 are going to go by pretty quicker. Here's another one. R equal 4 sine theta. So if I multiply both sides by r squared, that's the same as x squared plus y squared. R sine theta, that's the same as y. And if I get everything onto the right, then I'm going to have to complete the square next on the y terms. I'm going to keep x squared as is. Now remember, in completing the square, we want half of the number in front of y squared, and we're going to add that to both sides. So in this problem, I've got a negative 4 in front of y. I want half of that number, which is negative 2, squared. Negative 2 squared is 4, so I'll need to add 4 to both sides. Now why I would do that is because in completing the square, after you've figured out which number to add to both sides, the expression that is in parentheses is always going to factor, and the factors are always going to be the same. So y squared minus 4y plus 4, that's going to factor as y minus 2 times y minus 2, or y minus 2 squared. And now at this point, I'm done manipulating the equation. I'm now in a rectangular form here. And I'd want to recognize that this form is a circle, right? The standard form of a circle is where you've got x minus h squared plus y minus k squared equals r squared. R is the radius, 2 squared is 4, so I'm going to be drawing a circle with a radius of 2. And the center point would be located at hk. H is 0 and k is 2. So here's the center of the circle at 0, 2. And then I'd go 2 units above the center, 2 units below the center, 2 units to the left of the center, and 2 units to the right of the center in order to plot like 4 additional points and then draw that circle there. Okay. By the way, because we don't have a rectangular grid, we got a polar grid here, going 4 units to the left and to the right may be difficult to see, but actually you're going to be on the pi over 4 axis and the 3 pi over 4 axis. So to figure out where to locate that point, all I would do is I would let theta be pi over 4 and then let theta be 3 pi over 4. Sine of pi over 4 is 1 over root 2. Times 4 would be 4 over root 2. If you were to rationalize the denominator then, you would get 2 root 2 for r. Now root 2 is roughly about 1.4. So 2 root 2 would be roughly about 2.8, which means that on the pi over 4 axis, I need to go out roughly about 2.8 units. And using symmetry, I can do that on the other side here on the 3 pi over 4 axis, go out roughly 2.8 units to get to that other point there. Okay. Problem 6 will be a similar deal here, and then I'm going to have to complete the square. So r2 cosine theta, what does that look like in rectangular form? Well, if I multiply both sides by r and use my conversion formulas, r squared, that's the same as x squared plus y squared. R cosine theta, that's the same as x. Okay, and if you get everything onto the left and complete the square with the x terms, I'll leave y squared as is, then we want half of the number in front of x squared. Half of negative 2 is negative 1. Negative 1 squared is 1. So I'll need to add 1 to both sides here on the next line, and I've done that. That will allow me to factor the expression that is inside the parentheses. X squared minus 2x plus 1 is going to factor nicely as x minus 1 times x minus 1, or x minus 1 squared. And so I'm looking at x minus 1 squared plus y squared equal 1, and at this point I'm now done manipulating the equation. I want to recognize that this is a circle. The radius of the circle is 1. The center point is located at 1, 0. H is 1, K is 0. So I can then draw this circle. The center point is at 1, 0. And then use the radius, which is 1. Okay, so go 1 unit to the right, 1 unit to the left, 1 unit above, and then 1 unit below the center to gather up 4 points and then draw that circle. Again, on the polar grid, going 1 unit above the center and 1 unit below the center might be difficult to tell, but you're actually going to have those points be on the radial lines pi over 4 and 7 pi over 4. Okay, so to figure out where on the pi over 4 axis you'd be plotting that, you would just simply plug pi over 4 into your equation there for theta in order to get r. Let me do that. Cosine pi over 4 would be 1 over root 2, times 2 would be 2 over root 2. 2 over root 2, if you were to rationalize the denominator, that would give you root 2. Root 2 is roughly about 1.4, so r would be roughly about 1.4. And on the pi over 4 radial line then, I'd want to go out roughly about 1.4 units and plot that point. Using symmetry, on the 7 pi over 4 axis, I would also want to go out roughly about 1.4 units and plot that point. Now, the next group of 6 is going to kind of take some more work. So the first 6 were fairly easy in that we could just identify, hey, we're drawing a line or a circle. Okay. So let's take a look at some of these other ones. Now, before we do that, actually, a lot of polar graphs are symmetric to an axis, and so here's the information about symmetry for polar coordinates. If you want to test the graph, just like symmetry in algebra, you're testing for whether the graph is symmetric to the x-axis, the y-axis, or the origin. The x-axis is the same as the polar axis. The y-axis is the same as the vertical line theta equal pi over 2, and the origin is the same as the pole. Okay, so if you want to check if the graph is symmetric to the polar axis or the x-axis, you're going to replace theta by a negative theta and then check and see if you get the same equation. If you want to check if there's symmetry with respect to, is what WRT means, with respect to the vertical line theta equal pi over 2, or the y-axis, you're going to replace theta by pi minus theta and check if you get the same equation. And then if you want to check if there's any symmetry with respect to the pole, you're going to replace r by a negative r and check and see if you get the same equation. Okay, so we'll need to use that in several of these problems coming up here. So let's take a look at problem 7 next. I am going to begin by using a table of values and plot a bunch of points, and then after I've gathered a bunch of points, I'm going to then use some symmetry there to complete the graph. So let me start selecting some values for theta. Okay, like if theta is 0, cosine of 0 is 1, times 2 is 2 for r. Now remember, I'm plotting the point r theta, not theta r, so here would be the point 2, 0. If I let theta be pi over 6 next, 2 times pi over 6 is pi over 3. Cosine pi over 3 would be 1/2. Times 2 is 1, so r is 1. I need to go out 1 unit on the pi over 6 radial line and plot that next point. If theta is pi over 4, 2 times pi over 4 is pi over 2. Cosine pi over 2 is 0. Times 2 is 0. R is 0 there. So on the pi over 4 radial line, I need to go out 0 units, or that's going to put me right at the pole. I'm going to select pi over 3 next. So cosine of 2 pi over 3. Well, cosine of pi over 3 is 1/2, as we said earlier. If you flip that triangle that was in quadrant 1 over into quadrant 2, then that's going to affect the adjacent side, and that it's going to be a negative. Okay, so cosine of 2 pi over 3, that'd be negative 1/2. Times 2 is negative 1. On the pi over 3 radial line, I need to go in the opposite direction 1 unit. Okay, so there's that next point. Let me take theta to be pi over 2 next. 2 times pi over 2 is pi. Cosine pi is negative 1. Times 2 is negative 2 for r. Okay, here's the pi over 2 axis, one of my major axes. I need to go in the opposite direction 2 units, and so I'm down here. Next, I'm selecting 2 pi over 3 for theta. 2 pi over 3 times 2 is 4 pi over 3. Cosine of 4 pi over 3. Well, if I had cosine of pi over 3, that was 1/2, as we said earlier. If you flip that triangle into quadrant 3, which is where 4 pi over 3 would be at, then that's going to affect the adjacent side and the opposite side, which I don't care about the opposite side, but the adjacent side would be negative 1. Okay, so cosine of 4 pi over 3 would be negative 1/2. Times 2 is negative 1. Okay, so here's the 2 pi over 3 radial line in quadrant 2. I need to be going in the opposite direction 1 unit, and so that'll put me at this point here. Next, I'm selecting 3 pi over 4. I just get a couple more values here. If you plug that in, 2 times 3 pi over 4 is 3 pi over 2. Cosine 3 pi over 2 is 0, so r would be 0. On the 3 pi over 4 axis, I need to go out 0 units, so that'll put me at the pole. Okay, so far I've got this curve that's kind of creating this little loop here. And if theta is 5 pi over 6, plug that in. 2 times 5 pi over 6 is 5 pi over 3. 5 pi over 3 is in quadrant 4. Now cosine of pi over 3 is 1/2, again as we said earlier. Now if you were to flip that triangle into quadrant 4, that's going to affect the opposite side, which we don't care about for cosine of an angle. Cosine of 5 pi over 3 is still going to be 1/2. 1/2 times 2 is 1, so r would be 1. Here's the 5 pi over 6 radial line. You'll go out 1 unit on that and plot that next point. And we'll just take one more value here before we use some symmetry. If theta is pi, cosine 2 pi is 1, and times 2 is 2. Okay, so theta would, or r would be 2. On the pi axis, I need to go out 2 units. So here's what I got so far. That line that's that curve that's drawn in pencil there. And of course I could continue using the table, you know, but at this point I want to check and see if the graph is symmetric to the polar axis, okay, the x-axis. To do that, I'm supposed to replace theta by a negative theta in the original equation. So I've done that, replace theta by a negative theta. Cosine of negative 2 theta, that's the same as cosine 2 theta, right? The cosine function is an even function, and so I would get 2 cosine 2 theta for r. Well, that's exactly the same as the equation that was originally given to me, right? So this calculation tells me that this graph is going to be symmetric to the polar axis. So basically what I have here currently in pencil, if I rotate about the x-axis, I can produce the rest of this graph, which I've got drawn in red. Okay, and I also drew that graph here on my actual polar graph paper, so you can see that. But what we're looking at is a 4-leaf rose. Okay, now after we've looked at doing some graphing by hand, I'll comment on some of the famous polar graphs, and this is a famous curve. I mean, what I mean by famous curves is like in algebra, there's some curves that you know by name, like a parabola. Everybody knows what a parabola is, or what the shape looks like. Okay, it's the same deal here with polar coordinates. Like there's some curves that you do lots of things with, and they have a name to them. Okay, 4-leaf rose would be one of them. A cardioid is, we'll look at that in the next video. A lemison. Okay, some of these are like they're common curves when it comes to polar coordinates. Okay, and I'm going to go ahead and stop right there.